In addition to following a bimolecular elimination reaction pathway, elimination reactions can also follow a unimolecular elimination reaction pathway. In this case, the rate of the reaction, just like in an SN1 reaction, is dependent only on the concentration of the substrate, not the base. In this example, because the substrate is the only compound that's reacting, the first step is the leaving group comes off. This will generate a carbocation. In this example, we will have a secondary carbocation like this. There are two carbons connected to this positive charge. From here, a base will come in. All right, that is B- with a lone pair. It can abstract a proton, which will then form our double bond. So again, this is a unimolecular reaction because the rate of the reaction depends only on the substrate here. This is stepwise. There are two steps in this reaction. Just as in E2 reactions, an E1 reaction is sped up by a larger substrate. Let's think about why. If we have this primary alkyl halide and we take off our leaving group here, we end up with a primary carbocation, which is not very stable. If we have a secondary substrate, the leaving group will come off. We now have a secondary carbocation, which is more stable. If we add even more steric bulk to this, we make the substrate larger to this tertiary alkyl halide, take off the leaving group. We now have a tertiary carbocation, which will be the most stable because it has more opportunity for hyperconjugation. In this case, because this tertiary substrate is the most stable, it's also the most reactive. E1 reactions are also regioselective. The location of the double bond formation depends only on the substrate. So in these examples, we're only going to have the Zaitsev product, which is the more substituted alkene. So let's take this example that we've seen before. If we were going to follow an E1 mechanism here, the first step is we would remove the leaving group, which would generate a carbocation right here. Then we would abstract a proton from the beta site. There are two beta sites. One is here, one is here, but we're going to remove the hydrogen that will give us the most substituted double bond, which will be this one here. So our base will come in, grab that, form our new double bond to give us the more substituted Zaitsev product. Another example, if we have this example from the text, again, we're going to lose our leaving group first and generate a carbocation. It will look like this. There are three beta sites here, two identical sites on the left and the right, and then one on the top. If we remove the hydrogen from the top, we're only going to have a di-substituted alkene. But if we remove one of the hydrogens from the left or the right, the alkene will be more substituted. So we're going to form that product preferentially. After the leaving group is removed, the base will come in, abstract a proton, generating our double bond, which will give us the Zaitsev product, which is the more substituted product. In this case, it will be a tetra-substituted product. E1 reactions are also stereoselective, which means we're going to favor the trans isomer over the cis isomer as our product. In this example, we will remove the chlorine, our leaving group, to generate a carbocation. Right here, we'll then look at the two beta sites. There's one here and one here. The one on the right would give you a less substituted product. That won't be favored, so we're going to eliminate the hydrogen atom on the left, which will collapse down to form a new double bond. There are two products that we can make. We can make the cis isomer, which would look like this, or the trans isomer, like this. Because the trans isomer is less sterically hindered, it will be more favored. There's less steric clash between those two methyl groups, so the trans form will be favored in this case. Finally, you can also see carbocation rearrangements in E1 reactions. This is a little bit more complicated. We remove our leaving group here to generate our carbocation. Now in this case, we have a secondary carbocation. It would be more stable if we could somehow make the carbocation on this part of the molecule. So what can happen is the hydrogen on this group here can actually shift. If it shifts over, we generate a new carbocation. So let's draw that again. So we've gone from a secondary carbocation to a tertiary carbocation, which will be more stable. So in this case, because we generated the carbocation, this is not a concerted process. We generate the carbocation, which can then rearrange to give a more stable carbocation. Now the base will come in and abstract a proton and form the more substituted alkene. Just like that. This is an example of what we call a hydride shift, because this H, along with its bond, are going to move over to the carbocation. We have an example here where we can also have a methyl shift. Again, we're going to remove the leaving group, generating a carbocation. In this case, just like before, we have a secondary substrate, which is not as stable as a potential tertiary substrate, but we don't have a hydrogen that can move. Instead, we're going to take this methyl group, it will shift, and we will generate the same carbocation. We have a tertiary carbocation now, and we're going to have that methyl group in the place of the secondary carbocation. We will now do a beta elimination of the hydrogen, which will form our double bond and give us the more substituted product. In this case, this is a tetra-substituted product, something you wouldn't expect if an alkyl shift had not occurred.